Alright, hey AP Chemistry. I just wanted to make a brief video on something that we talked about in class having to do with calculating the rate of a reaction using stoichiometric coefficients. So I wanted to remind you of this equation, and I said it a couple of times. This is equation 14.5, and this is in your text in chapter 14. Specifically, if you want to know where equation 14.5 is found, it's found on page 627. This is on page 627 in your textbook intro. Okay? So if I have a generic balanced chemical equation, little a, big A, little b, little c, little d, those are my stoichiometric coefficients. If I have little a, big A, plus little b, big B, yields little c, big C, plus little d, big D, right, and my reactants and products, I could write an average rate of reaction in the following form. The average rate, and I'm going to write this on the side, this is kind of like the average rate of the entire reaction. Average rate of reaction, RxN. So the average rate of the reaction would be -1 over A, change in the concentration over the change in T. It's also equal to, these are all equal to -1 over B, change in the concentration of B over the change in T, which is also equal to a positive 1 over C, change in the concentration of C over the change in T, and then which is also equal to positive 1 over D, change in the concentration of D, change in T. And just to make a note, my right side, my C's here are my products. These are my products, and they should be positive. And these are my reactants, and they should be negative, the rates of those reactants, right? And what each of these things are saying, and I'm going to focus on this whole thing, this, like, let's say I'm just looking at this B business. -1 over B times the change in B over the change in T, that should equal the whole rate of the reaction. If I just wanted the rate of the consumption of B, I would be looking at this, okay? That change in B over the change in T, which is the rate of consumption of just B, that's going to be negative. Reactants get consumed, which means they get used up, so this change in B would be decreasing or it'd be negative. Products get produced. So if I wanted the rate of production or of appearance of D, I would just be looking at this. This is the rate of production or appearance, sometimes called appearance, of D. And this is known as the rate of reaction or rate of reacted or disappearance of B, right? And so that's convention. If I'm looking for the rate of appearance or disappearance or the rate of production or reaction of a certain reactant, I'm only looking at the change in delta B over delta T, that whole thing. This -1 over B, if I multiply by this -1 over B, that should give me the overall average rate of the reaction, okay? So now I want to do an example, kind of similar to what we had in class. So this is question 30 from your exercises. Question 30 says, consider the following reaction. I have 8H2S, 4O plus 4O2 yields 8H2O and 1S8, right? There's like a hidden 1 there, okay? Now, it wants me to complete the table. It already gave me the change in H2S over change in T rate, which is, this is the rate of consumption or disappearance of just H2S, okay? And so, where did that come from? If I want to write a generic rate equation from this balanced chemical equation, I would write it like this. The rate, overall average rate, is equal to -1 over 8, change in the concentration of H2S over the change in time, which is also equal to -1 over 4, change in the concentration of O2 over the change in time, which is also equal to +1 over 8, change in the concentration of H2O over the change in time, which is also equal to positive 1 over 1 change in the concentration of S8 over the change in time. How did I do this? I got the 8, the 4, the 8, and the 1 from the balanced stoichiometric coefficients, and I'm just writing change in H2 over, or change in whatever, change in H2S over change in time, change in whatever. I'm basically writing the generic form change of whatever concentration over change in time. Now, I was given that the change in H2S over change in time is equal to negative 0.08 molar. I was given this. That's what I was given. I wasn't given, this whole thing does not equal the minus 1/8. That's when I want to solve for the rate. I'm gonna kind of skip to the end. I want to solve for the rate. If I want to solve for the rate, I'm just going to use this part of the equation. Like, this is my rate, this is like my average rate of the reaction. When they say rate at the end, it's like, overall, what is the average rate of the reaction? And all of these numbers are equal to each other. And the only way we get them to be equal is by multiplying by this fractional coefficient. So let's say I want to solve for the rate. Rate is going to be equal to negative 1/8 times whatever was given to me. Change in H2S over change in T, which is equal to negative 0.08 molar per second. If I multiply this times 1/8, negative 1/8, I should get a positive number. My overall rate of reaction should be positive. All right, so my rate of the reaction, negative 1/8 times 0.008, that's like saying 0.08 divided by 8. I should get positive 0.01 molar per second. If I wanted to get it back, I'd have to multiply by 8, and I get my 0.08. So my rate of the overall reaction should be 0.01 molar per second. I did that by multiplying negative 1/8 times 0.08. I kind of skipped and said, that's how you figure out the overall rate. Rate is equal to this, it's also equal to this, it's also equal to this, and if I kind of break it down by sections, all of these have to be equal to each other. So basically, this must equal 0.01, this section must also equal 0.01, this section must also equal 0.01, and this section must also be equal to 0.01. That's what I mean by how are they all equal? They're all equal to each other using these stoichiometric coefficients. Now that I know that my rate is equal to all of these sections, I mean, I could easily solve for the rate of, I could easily solve for this rate, 1 over 1 change in S8 over change in T. It's equal to my rate, which is timesing by 1. So if this is my rate, let's say I want to solve for change in S8, I know my rate is equal to 0.01 molar per second. I could set it equal to 1 over 1 change in S8 over the change in T. And then I don't really need to do anything with this 1 over 1. I mean, it's multiplying by 1. Basically what this is saying is the change in the concentration of S8 over the change in T is also equal to 0.01 molar per second. And the rates are always in the units of molar per second. Always. Make sure you make a note of that. Right? What does change is the rate constant, and that depends on my reaction. And the change in the rate constants will have to give me the unit of the rate of molar per second. The last two that I'll do, and I'm going to have to erase this, the last two that I'll do is how I could solve for O2 or H2O given my initial rates here. So let's say I started backwards and I went, okay, I know that my rate of H2S times change in T is equal to 0.08. That's what this is. And this must equal this. So I'm going to say negative 1/8 times the change in H2S concentration over the change in T is equal to negative 1/4 times the change in O2 over the change in T. Okay? And so I'm setting these two equal to each other. These are all equal to each other. And this quantity equals 0.01, and this quantity equals 0.01. The whole thing when multiplied by negative 1/8 or negative 1/4. But let's say I didn't know that. I'm going to plug in this number of 0.08 to here. This is 0.08. So I'm going to do negative 1/8, all right, times negative 0.08 molar per second equals negative 1/4 times the change in the concentration of O2 over the change in time. Okay? Now I have to somehow solve for this. This part of the question only wants change in O2 over change in T. Well, algebraically, if I want to do that, I can multiply negative 1/8 times this, and then eventually multiply by 4. So algebraically, if I'm continuing this, I'm going to do my negative 1/8 times negative 0.08, and that gives me 0.01 molar per second. Okay? And that's going to be equal to negative 1/4 times the change in concentration of O2 over the change in T. And if I want to solve for this, I have to isolate that whole thing because it wants just the change in O2 over the change in T. If I want to solve for this, I have to multiply both sides by negative 4. Because that's how I get rid of this negative 1/4. Dividing by 4, that's what negative 1/4 means. To get that away, to isolate negative 1/4, I have to multiply by 4. So I'm multiplying both sides by negative 4. And I will get negative 4 times 0.01 molar per second. And it looks like my change in the concentration of O2 over the change in T is going to be equal to negative 0.04 molar per second. And I'm going to put that here. Negative 0.4 molar per second. And now, I'm going to make you check your answer, but I'm going to tell you right now that the answer to the change in H2O over the change in T should also be equal to positive 0.08 molar per second. In order for you to check to make sure you understand this, I want you to check to make sure that you understand that you're getting the change in H2O over the change in T is equal to 0.08. Hopefully this was a nice little crash course on how to do rates of reactions using the stoichiometric coefficients. It's not going to be the major part of chapter 14, but there are definitely going to be some questions that you have to answer that talk about the rate of appearance or rate of disappearance. And you'll see this in a future lab. All right, so if you have any other questions, comments, or concerns, please let me know.